That's all I have to say here. So we're going to go ahead and switch over to Zbyszek Otwinowski. So we're going to talk about scaling and merging.
Yes, okay. So the thing is, we talk about essentially how we how to get essentially from spots into structure factors squared, and possibly we are getting associated with it some estimate of uncertainty. But the question is, we get a lot of those measurements, and some of them may get more than one observation of the same HKL index, or we may have more than one observation of symmetry-related indices. And so the thing is that we have to kind of somehow add those results from this observation, and this adding will be fine if they will be on the same scale, and then, but it's often we find that they are kind of the relative scale between those observations can vary. And also, when we do, this is an issue which is we often encounter, that our crystals are maybe not absolutely perfect. So essentially, for example, this crystal, if one looks at this diffraction pattern, you can see that there are two distinct maxima. And this will be, but because they're so close, that there will be integrated essential spun reflection coming from a crystal which is slightly split. So we may have all kinds of factors contributing to our measurements. And so I will be talking about how to deal with those various issues and recognize their impact on our results. Okay, so kind of sorry for this kind of busy slide, but the thing is that we have our structure factor squared. This is what we want to determine, and we have a Darwin equation which relates it to the observed intensity. And it's, of course, actually beam intensity is kind of primary factor, but also, for example, how fast we rotate the crystal, essentially how fast the crystal gets to Reval sphere. This is this kind of funny term. But we also have to think like it's the crystal volume in a beam is, of course, it's another factor which gives us the intensity. If we have smaller the volume of the primitive cell, the diffraction will be weaker, and we also detector measurements will be to count. It has to be absorbed in the detector, and also there will be kind of additional factor that is detector may have somewhat uneven sensitivity in different parts. For particularly CCD detectors have this problem. So we have kind of a whole group of factors which relates our observed intensity to the structure factor squared. And of course, those parameters may easily vary between different observations. So the question is what we do. For some of them, we can calculate them from geometry. So we get some whole group of those factors or from, say, outside calibration of the detector. And, but the rest, we simply say, okay, but we'll adjust those scale factors. So different measurements, we agree as well as they can, because there's always some noise and other issues. So so this process of putting all measurements on the same scales is called scaling, and essentially every data analysis in macromolecular crystallography has to go through this process. But also in this process we will also merge reflections, and this will be kind of major part of this discussion. So essentially how we do scaling is this is a very general approach, which is essentially that for each observation, each HKL index, but each instance of HKL index means we have some kind of property, for example. This would be property associated with absorption, or which depends on geometry, or any other of those factors, maybe depends on some particular circumstances of the observation. And then we say, okay, but those parameters may have a non-scale factor, that maybe we should kind of move absorption up or down in particular directions. So how we do it with it. So one of the things which we have to account for is decay. This is one of the big problems is that for macromolecular crystallography is that crystal the fraction gets weaker and weaker over time, and this is get weaker in resolution-dependent fashion, and in fact it's okay. So we have used in somewhat inconsistent terminology between different people. This is the star vector according to James. But the thing is that essentially this is the factor which is defined like the star or vector squared modulus divided by 2, and then because we are taking exponent, this will be classical formula for B factor as applied to intensity. And the thing is that the model in HKL is to apply separate B factor for each batch of data, and it's with maybe additional restraints so the fluctuations are not too big. Okay, so what happens is now the experimental circumstances can be that that we have a beam which is larger than the crystal, and then what was observed by lots of people that essentially scaling B factor goes roughly proportional with frame number, which in this case would be proportional with dose because we typically give fairly uniform dose, and scale factor is fairly uniform, so it's essentially decay described by B factor. And then people also notice that this is conveniently relates to units of radiation dose, that for most protein crystals, the process that's kind of causes decay, which is essentially random displacement of atoms, is fairly uniform because all proteins are built roughly the same way, and typical solvent is mostly water. So it's about 10 to the 6 gray per 1 angstrom square increase in B factor. And so this is but this is true for crystals which are cooled to about 100 Kelvin. Okay, this is again those complex formula are essentially polynomials in direction cosines. So this is to describe absorption. Essentially, absorption. We say, okay, it's some way of kind of a simple polynomial in different directions, and then those coefficients pi will adjust to improve merging of relative reflections. This is kind of well described in the literature. And we have immediately kind of interesting check that if we have real absorption, then the absorption has to be the same in opposing directions. If you go for the crystal, which is corresponding to spherical harmonics being even. So, but what is interesting is that, and this is general property of scaling, that often one parameter captures scale factor coming from some other source. And so this is a kind of, if we see that non-zero coefficient is probably okay, some other kind of, something other property was changing during the experiment. And it's so this is sometimes kind of a good way to monitor kind of consistency of the whole systems of equations. And the thing is, this correction for absorption can be really precise. This is a kind of one test which is kind of prompted me to introduce this correction, was data from chymotrypsin where merging scale factors from really kind of strongly reflecting crystals were really poor, means about 10% overall. And then after introduction of absorption, the scaling merge factors went down to kind of really quite nice, and if you treat it by separated, at low resolution they're about 1%. So, and then the structure was very easily solved from surface scattering. But this is kind of in good old days where we had image plate detectors, and some people still have them. They are kind of somewhat more precise than CCD detectors. Okay, so what are the kind of other options that, for example, I think we may have unstable beam, essentially that its rotation speed of the crystal would be nice to be constant. And now the problem is the mechanical engineering of this issue is in practice somewhat complex because lots of people use DC servo motors, and servo motors have tendency to oscillate, and this is particularly a nasty issue. And and some beamlines, but I think nowadays it's mostly solved, this problem. But sometimes still occurs, I mean, sometimes. And so there is kind of a special option to correct for this issue. Okay, so what else? But now we're kind of going to, okay, so we'll assume that we already scaled all our observations, and now we have to merge them. And this is part of the process that is rather complex, because we'll try to understand what happened in the experiment. And it's often really the first step where we really get kind of a good assessment of what happened, because looking just at the diffraction image, okay, you can see that if you have no data, that's easy. But if you see lots of diffraction spots, it's very hard to say how accurately they will be integrated, and particularly will you see a phasing signal. And also, I mean, like Jim mentioned, that metric symmetry, the symmetry of the lattice, may not necessarily tell you symmetry of diffraction pattern. So another thing is what we have to estimate, essentially uncertainties of your measurements. And you may have kind of some idea how they should be on a typical well-made experiment, but sometimes a particular experiment may have problems which are less frequent, and you may have to adjust your error model. And then probably the biggest issue, which is kind of like we've seen on this diffraction pattern from which we started this presentation, that there may be more than one crystal type present in a beam, and particularly if you have variations in exposed volume. Say when crystal rotates, say one of the crystals may get in and out of the beam, and you may have, for example, not perfect isomorphism between structure factors of what you observe. And also another aspect of Heisenberg principle in action is every time you observe an object, it's getting altered. This is called radiation damage. And part of it is decay, which is corrected in scaling, and part of it is radiation damage, which is non-decay ones, which is some alteration in the structure. And so we have all kinds of events going on, and we have to differentiate them in merging analysis. And we also kind of like to see if we have what we would like to see for a particular phasing signal, signal for strange reason called anomalous signal. It's really should be called kind of consequence of absorption. And also we may analyze systematic absences, which would indicate the space group, and all kinds of potential pseudo symmetries, which are another kind of complicating aspect. So this feature is unique to HKL, but there are kind of other approaches are roughly equivalent to it. That is essentially what we do is, if we have lattice which is say trigonal, it means there's highest possible point group symmetry, or P6 plus if we don't have Friedel symmetry. And then it has all kinds of subgroups. And the program scales data starting from P1, and then increases symmetry to all next symmetries, and then say to monoclinics, and or P3, and then again to higher symmetry, like P3 to 1 point group, and or from P3 to say P6. And then the thing is, we look at if the goodness of this statistic, expectation of kind of our model, expectation of errors, agrees with expectation with observed differences, which are with the symmetries, and when additional factors. So we look at what is the increase in goodness of fit on the additional kind of conditions imposed by higher symmetry, and also we count how many of those conditions are present during merging. So if you say if this number is 1%, it means that we simply don't have indication of higher symmetry. Simply, we didn't acquire yet enough intersections in the reciprocal space. So for this is if you have very partial data set. But this goodness of fit 500 means, okay, it's really horrible disagreement, we expect it close to 1. So it means that this indicates that this phase group is not Lowry symmetry is not present in the data. So again, but then there's also the issue of if we decide on the symmetry of a crystal, then there is the next issue. So what should we do with estimating uncertainty of our measurements? And one approach, which is simple, okay, let's try to solve a structure, see what happens, let's progress it, means rely completely on default assumption. And in fact, if it works, why not? In a sense, one shouldn't spend too much time on kind of analyzing something that is not a problem at all. So but I think why we have this meeting is that because often this doesn't work, that there are all kinds of problems showing up during merging analysis, and then we have to kind of think what's going on. And essentially, I think the main issue is that there could be many problems present, and it requires some kind of experience which of the problems may be kind of causative in particular case, and what is the approach to address this problem. Sometimes it's a better estimate of error, like the vibration of a crystal, which was discussed. It will increase the scaling uncertainty. But this could be problems with isomorphism or radiation damage. On the other side, for example, if you have data where there's no anomalous signal at all, we can simplify our assumption that essentially our Lowry symmetry is higher, that essentially the diffraction pattern is centrosymmetric. So essentially if the effect is weak, we can assume that essentially non-existent is not perturbing our assumptions. If it's large, then we should add it to our assumptions. So that's why this is a rather complex process. So what we do? So we calculate our goodness of fit or chi-square statistics, where we compare observations to the kind of average of all merged observations. We divide it by the uncertainty of the difference, which is that essentially sum of uncertainties of reflection and average. And then we correct for the fact that the average is not independent of this observation. So there is essentially we have n-1 degrees of freedom if we have n observations. So this statistics for a good error model should be 1 if projected on various aspects like resolution or intensity. And this is a case, and this statistics we can also calculate under assumption that we have an anomalous signal or not. And this is a case where one would look at the merging artifact and say, okay, it's not particularly bad. It means its size is kind of something like 3% low resolution goes to 18% to angstrom. But if we look at the chi-square statistics, we see, oh, no, it's clearly underestimates errors, that there is something going on, and we can try to identify the source. And so, and then once we we identify the source, we can essentially redo this analysis with this source accounted for, so now we can better extract other potential sources of errors or other signals. So this is and part of this iteration has been now automated in HKL 3000, or 2000 really also. So the thing is, what is it's really important to have a good model of this problem. This is a particular issue for if the crystal structure factor change during exposure, because how do we what type of model we have? So we have a model that is about the expected magnitude of this change, and unfortunately it's a different change for every unique HKL. So this is a rather complex model in case of radiation damage. The question is it uniform with those or not? And we published some paper which analyzed the fact that it tends to be uniform with those, this change. Even if it's one would expect some nonlinearity, this nonlinearity is relatively mild. But also we have to it's more complex if we have different crystals. How do we assume what is isomorphous to what, in a sense? And also kind of things like vibration of the crystal is a bit different error model if crystal simply is non-uniformly rotated, but the rotation axis is fixed. So essentially it's only one-dimensional random rotation of a crystal. But if crystal vibrates in the air, it has essentially two-dimensional random path. So there are all kinds of additional uncertainties depending on the particular situation. And I think it's very important not to create models which are too complex, because then the calculation time will be longer, but sometimes it's acceptable. But the second aspect is that calculations are not guaranteed to be stable, and these very complex models may kind of also be affected by error. Essentially, that is kind of this can soak in error and follow the noise rather than real signal. While the models which are too simple will simply kind of not account for something which is important. So this is so what we assume. The default error model, which I think is kind of more or less standard in the field, that is, we have about 3% error, kind of, which is assigned with multiplicative factor. And it's, for example, this could be a component of calibration error of a detector, or it could be kind of various inaccuracies, for example, in spindle alignment and kind of how we kind of adjust boxes to capture. I mean, it could be part of the reflection tail, maybe varying a bit between reflections and so on. And sometimes this is 3% tends to be on the good side. So this parameter sometimes needs to be adjusted upwards because, say, spot profiles are really highly variable and you don't account for their variability. But if you have to go above 10%, then something is really wrong. And probably it's not a multiplicative error, but rather a different type of error. And also, if you have to go, it's usually associated with bad spot shape or some crystal vibration. And the scale factor, and this is kind of, the error models are complex, so we end up kind of adjusting estimates of the error, and 1.3 factor default values for CCD detector, which have a complex pattern of fluorescence and being spread out in a phosphorescent kind of geometric correction. And in fact, the scale factor tends to be below, just about 1 or slightly below for plateaus. I mean, so it's where we have better model of Poisson statistics. I mean. And if you have to increase it, it means that there was again, we are kind of accounting for other effects. If you go above 2, it means something which is, either means that we have a bad model of a detector, that essentially the detector is much more noisy than, and this, essentially somebody increase the numbers in the detectors, which is this gain factor. And it's, so this is, but rather not to increase it too much. And now, I mean, this is what was done before, but now we have this additional button called autocorrections, which is applying this complex error models and adjust parameters. And sometimes it works very well, but it does a lot of things at the same time. And we have to kind of now kind of write a better interface which will decompose those various effects. Because essentially what we do, essentially there is, to apply these various corrections, we need to kind of have expectations of various signals. So in particular, we found that, okay, crystals often are anisotropic to the signal, maybe very, say, decay much faster in reciprocal space in one direction than the other. So, and then what we found that if we make kind of sharpen the data so they are isotropic, the structure solution works often much, much better. Then, next thing which I will talk is informativity-based resolution limit. Essentially, we have to have some kind of resolution limit in our data. So essentially, when we consider data uninformative but past that resolution, and we realize that this idea may be expressed in somewhat different form. Then we have this radiation damage correction. Essentially, if there is a substantial change, and often is, change in the structure factor during exposure, we try to make them uniform. So default is not to extrapolate to 0 dose because this is, would increase errors too much. It's the other to have best structure solution, it's better to interpolate to middle dose in a sense. And there is this option to 0 dose extrapolation is not automatic. But then, we have benefit of automatic adjustment of error parameters, but this assumes that there is no error in symmetry assumption. But sometimes if we have, say, various crystals in the beam which come in and out of the beam, we may have this situation that there is a kind of internal non-isomorphism, and often this estimate is 0, but sometimes it's kind of 1 or 2%, which is typically okay, unless we have, say, try to get very anomalous signal. But they say something like 10% or 20%, which means that we have essentially a wrong symmetry assumption. But one great benefit of this kind of complex model is that it's much easier to identify outliers. I mean, particularly if we have anomalous signal in radiation damage, we can differentiate the presence of some signal which is a systematic signal from some kind of outlier measurement. So what are those estimates? The critical estimate is internal non-isomorphism. Here it's kind of quite high, about 0.03, which is 3%, but it is still much less than anomalous signal, so this which allows structure solution. And we also get kind of various statistics and so on, which is for people who like them. And okay, so what is the advantage of this correction, this X-ray-induced radiation damage correction? That is, without it, our agreement, this agreement between reflection was very high. So reflections measured at the beginning disagreed with the average. Reflection measured at the end also disagreed between the average, but they have slightly higher error model, so the chi-square was a bit better. But the one in the middle agreed better with the average. This is U-shape of chi-square statistics, this characteristic for radiation damage. And when we apply this radiation damage model, then we got a very nice agreement. You can see, oh, there was trace of ice going to you just make this agreement larger, some resolution shells. But essentially, we got, and the structure got solved from anomalous scattering of sulfur. And there are a few comments about identifying non-isomorphism within the crystal and particularly between crystals. That one of the things is that the unicell is not a good indicator. That it's, you may have essentially the same unicell and structure factor substantially different. You can have also the opposite if you have a situation where the unicells are poorly determined. So if you have a data collected only from short rotation segment and low symmetry space group, then the unicell may not be particularly well determined, while crystals may be isomorphous. So what is our measure between data sets is better measure, but the question is, it includes a lot of effects, and this could be, for example, anomalous signal, but also it includes experimental error. So this is, if you have need to measure many data sets, it's typically in situations where we are really at the margin of getting good data. So often we have rather large experimental errors, so then we have to differentiate between poor armature, which simply comes from the large random errors which we like to average, from differences which come from non-isomorphism, where we would like to put some limit to it. So this is an example from the tetragonal lysozyme. We kind of, it's going to be, you see, I acquired a large number of various data sets from various kind of testing procedures, and I found that there is a kind of a cluster with particular unicell version, but unicell parameters, but even within the cluster, when we started to compare the structure factors between those forms, then we realized that there could be really large difference between 24% del F over F between two data sets where the unicell difference is 1/100 of an angstrom. So it's and the thing is that this is the various, essentially, lysozyme molecule can rotate within this lattice form quite a lot. It still kind of produce alternative ways of forming crystal packing. It also may have been some variations in sample preparation. And so this is a warning that if you have with multiple crystals, you cannot be assured that they're isomorphic. You have to test for it. And you have to find kind of particularly cryocooling conditions which will give you reproducible the same crystal form. And we found very interesting props for good isomorphism between multiple crystals. If we get low value of mosaicity, it means that during freezing, only one crystal lattice is being formed. It means that the conditions are fairly robust with respect to variations, kind of minor variations like evaporation of solvent. So it means that there's a good chance that the next crystal, even with small variation, will be isomorphous to the previous one. Whereas if you get large mosaicity, something like of order 1 degree or even larger, let's say about 1 degree, it's often indicative of multiple lattices being formed during cryocooling. Very large mosaicity, like 3 degrees, is more indicative of kind of crystals not being kind of really being aggregates of various crystals prior to cryocooling. Essentially, the crystals kind of often can slip around some plane, on some particular plane. Another kind of interesting aspect, how much this correction for anisotropicity can improve particular projects. First of all, not all crystals have significant anisotropicity, but some do. And in this case, there was variations of something like almost 40 angstrom square between different directions. So I think along the z-axis, along the x-axis, it was quite decayed, whereas along the y-axis, it was the fashion was best order. And if we simply kind of get data treated normally, and we look at the results after phasing, kind of look very strange. We placed the correct model just to see how. That essentially the correct model is alpha helical, and you can kind of, it's not easy to guess that this is alpha helix. After anisotropic sharpening, the map was quite nice, and this is how we generated the model. So it's so this is, but why it's weird? Because essentially there was an interesting elimination of use of uninformative data during sharpening. Essentially, it was a kind of anisotropic or elliptical resolution limit was applied. So it's another kind of case which is, you can show that you have I over sigma kind of, if you look at the ratio say of I over sigma say 2, which is I think nowadays considered conservative. In the past was considered kind of rather kind of aggressive, I would say. But it is a fairly sensible estimate of where the resolution limit is. Then essentially in one direction it's more like 2.4 angstroms, another direction is more like 2 angstroms, and in the third direction it's more like 1.8 angstroms. So it's whereas if you take the I over sigma criteria for isotopic data, it would end up around 2.2. So it's so if we kind of, if you just look at the spherical shell data, the statistics, the intensity over sigma statistics are not best indication where to place resolution limit. So looking at the problem from an isotopic perspective, for those projects which have is important. And then if we kind of correct for those issues, we realize that goodness of fit is substantially worse for anomalous pairs, which is good, it means there is a anomalous signal present, and in fact this actually was solved after. And we also kind of show now the CC1.5 resolution dependence. I think again some people maybe put the resolution by a bit higher, but it wouldn't help much because those data would be very noisy. And also, another thing that is, for people who kind of talk about this table 1, it's kind of, the values are hidden somewhere in the zip file, which is essentially much easier to extract them from the zip file and add it to the final result. So now there is a question, what does this intensity over sigma statistics mean? And it can be defined by more than one way. And in fact, even this average intensity over average sigma, some people look at it from perspective of average intensity to sigma, which is not exactly the same number, but very close in practice. And this is what I call executive criterion. That it's essentially, for example, when you have to put detector at some distance, we want to capture resolution up to some resolution limit. Somebody may decide, okay, that this resolution limit, its values maybe should be, say, I don't know, 1 or kind of what is the lowest limit is being recommended right now by some people. But I would say around 1 is I wouldn't push it past. You go down to lower than 1, and sometimes you have advantage of the detector being further back and reduce background. But the thing is that this is good for something that you have to do for the whole data set. But if you do look at the individual reflections, you can find a better criteria. It's also a good criterion if you have fairly uniform error model. So essentially, if all reflections, say a particular resolution, have fairly similar uncertainty. And this happens if you have, say, high redundancy. But there are exceptions. Sometimes it's hard to get high redundancy. And some measurements may be made under unfavorable conditions, for example, when the crystal was decayed. And so we can look at it, it's essentially, so we look at not our actual measurement of HKL, but rather expected value for this intensity, which is, and divide by sigma. Saying if you invert this equation, this would be equivalent of normalizing sigma to ease, essentially so-called E-value. So you can look at this as a perspective as from normalized structure factor and normalized uncertainty of the structure factor. And I think we like to propose it as a kind of being accepted as a new approach to resolution limit. And number of projects we've seen really nice improvement in maps and models. But there creates some issues in table 1 statistics. And just to show it how it looks like, so this is an example of particular data set and just one line of reflections along the line 0, 2, and L index. And at low resolution, the reflections have kind of small uncertainty, and this uncertainty goes up as we go to higher resolution. But uncertainty is not uniform for every measurement because of some differences in measurement conditions. And so this informativity criterion looks at the uncertainty size. It doesn't look at intensity of this observation. It simply looks at uncertainty, normalized uncertainty. If it exceeds, say, 1/2, then those particular group of reflections will be rejected. It's rather accidental that they have low intensity, but it's okay. So, and now just like to make a comment that for projects that we can produce reproducible crystals, and we have problems solving a structure from one crystal. Essentially, the problem is that on one side we need better counting statistics. That's why we need multiple crystals. On the other side, most of the time when we have a problem, the barrier is from some kind of non-isomorphism, which happens between crystals and during exposure. But this gap really depends on kind of particulars of each project. And understanding it, I think, is very important to push those projects to the very limit. So what are the challenges in data processing, which I think will be discussed also later, and in practicals? And we really kind of like to see some data which is kind of have those challenges. And so essentially that the single crystal is not sufficient, and or we have kind of insufficient phasing signal, kind of just at the limit, or we have anisotropic diffraction limit, which is kind of now we can see if we can deal with it better. And if we have non-isomorphism by radiation damage, or non-isomorphism within a crystal induced by radiation cooling and between crystals. And also kind of issues like problematic macroscopic order, for example, twinning or merophilial twinning or packing disorders. And just a comment about what happens if you use microbeam if you have these problems. And microbeam is justifiable if you just have small crystals, or potentially if the crystals have kind of long needle morphology. But if it's kind of other problems, particularly with quantic statistic limitation, microbeam will produce pure diffraction, so it will not help. And what is kind of non-intuitive, that the small beam may amplify problems coming from internal isomorphism, particularly when we look at the phasing signal. Because if you have a large beam, it will always see the same type of average between different crystal forms in the beam undergoing uniform radiation damage, so which can be nicely corrected, and then we can get extract well the phasing signal. If you have used microbeam, then they maybe have a complex variations, which is really hard to model because there is no kind of simple mathematics to describe what can happen. So this is. I'd like to thank particularly Dominika, Marcin, and Władek, and people kind of who helped me with additional data sets, which is most of this work was done using data sets which were provided by various people. I'd like to thank.